The Hooke's Law activity setup is really simple. It just consists of a spring. So here's my spring hanging down, and we're going to hang weights on it, and we're going to see how far the spring stretches. And then Hooke's Law says it will be proportional to the force we put on it, and that's all in our lab notebook, which you'll see later in this video. So the first thing we need to do is measure the distance from the bottom of the table to the top of the table to the bottom of the spring. Then we hang our first weight. I hang the 200 grams or 0.2 kilograms on the spring. Now I'm going to measure from the bottom of the table to the top. I put that in my table, and I repeat the process for 300, 400, 500, 600, and 700 meters. And that's really all the lab consists of as far as getting data. So I think if you watch the rest of the video on what to do with the data from the lab notebook that's coming up, you should be fine. Good luck. Here's what your lab notebook will look like. Your title, Hooke's Law activity, and these are the diagrams that describe the lab now that you've seen the actual physical setup. Your D0 in your table, and again I've given you the table printout. You can cut it in and tape it in your book. Your D0 is your initial height that you measure from the table with no weight hanging on it. Your DF is the distance that you measure from the table once you put a weight on, and it goes here. So in my example I have measured those two, and everything else is going to be calculated. So there's not a lot of data taking in this problem. And once you put these are the formulas you need for this lab, so write those down. That way you won't have to pick them out of your worksheet formulas. We're going to need our force is mass times gravity, which you already know. My delta X is just the difference. You probably don't need that formula. You know what that would be. The force on a spring. This is Hooke's Law. That's what the name of the lab is named after. Hooke's Law says the force of a spring equals a constant that never changes. It's based on how the material in the spring times the distance you stretch the spring. Turns out if you do the calculations, you figure out that the work of the spring, which I've made called WS for spring, is 1/2 K times delta X squared. It kind of looks like the kinetic energy formula, which we have on our worksheet. And the potential, U, don't ask me why, U is for potential, but it is. The potential energy in the spring is equal to the work you do to the spring. So that's always true. So once you find the work you've put in the spring, then you can just copy that number down for the potential energy. So to actually do the calculations, your force of the spring is just the weight of the force of gravity, which is the weight. So I just multiplied in this. I did it in black because that's going to be the same for you as it is for me, because you're going to use these masses here, hang them on the spring. So I have 1.96. My delta X, everything else I just totally made up. I did not even do a lab for this. I just made numbers up that seemed reasonable, so your numbers probably won't match this. But I measured those two, I subtracted them, and that goes right here. Then your K, if your force of the spring is equal to K delta X, then if you do a little algebra 1, you get K equals the force divided by the delta X, and I did that, and that's my 9.8. Then I just made these numbers up so I could demonstrate something later. And then the work of the spring, I use the formula 1/2 kx squared, and I get 1/2 9.8 times 0.2 squared equals 0.196. So you just repeat that process for all those masses. Then I'm pretended that I did that and I had all these numbers, because then step 8 tells us to do the following. Tells us to find the average K, and I really don't know how close together these numbers are going to be when you do the lab. We'll see. But we'll take the average and we get 9.81. Then I'm going to put the force in L2, the delta X in L1, use my linear regression, and I don't care about the B. It really should be 0, but it may not be. We'll see how the data comes out. And this slope really should match this. It'll be interesting to see how they compare. Then I did my percentage difference like we've always done. Then there's 2 activities I need to do to finish up the lab. I have some C-clamps and other tools that you can use as an unknown mass. Just come talk to me and I'll give you one. Then I measured the delta X. My K from above is 9.81. From up here, I'm going to use the average K. Then I just use this formula, plug it in, and I got that for my force. But I know the force of gravity is mass times gravity, so I divide by my 9.8, and that was the mass I got for mine. Now, mine turned out the same. Yours almost certainly will not. Your mass will not match your delta X. That just turns out how the numbers I picked worked. Then you're going to predict. You're going to put 0.05 kilograms on there. Okay, notice then I just multiplied 0.05 times 9.8, and it rounded to 0.5. And then so I predicted this distance. I pretended, I didn't actually run the lab, that's what my actual was, and then I did the same thing for 1 kilogram, and then I found the percentage differences. And that's what you should do. Good luck.